So while I wait for Bard to come out, I send myself in for the waitlist. I've already joined the waitlist. I will not be making any more comparisons in the what I call the battle of the bots because I believe it hasn't begun. The Bing work that I did for cardinality really told me that I'm going to stick with ChatGPT. So here's yet another chapter in ChatGPT does analysis or tries to. And this one's a little long because this chapter, infinite series of functions, was rather difficult because of power series. So I asked ChatGPT to define pointwise convergence for functions, and it did so. So it occurs independently at each point. Yeah, so convergence at each point. And then define pointwise convergence for a series. Yeah, and then it did so. That was fine. Then it gave me some good examples. That was very helpful. And of course, I read all this when I was reading for the chapter. Yeah. Then I asked it to expand on the pointwise convergence of a specific series. So it was x to the minus n, so 1 over x to the n. And it gave me how the radius of convergence is defined. Of course, this was really, I just wanted to see what it would say. And so I asked it for a non-positive radius of convergence. So it gave me one for which the radius of convergence is 0. So it's x equals 0. Then I asked it for an example of power series with negative radius of convergence. This is sort of like a litmus test. If, in a way, I wanted to know if, what it would say. Of course, it said the correct thing. There are none. The radius of convergence always has to be positive or equal to 0. Difference between absolute convergence and uniform convergence. Yeah, so absolute convergence refers to the convergence of the absolute value of a power series. And so yeah, here it goes. Gave me a nice conclusion. I really like the way ChatGPT answers compared to how the ChatGPT and Bing does it. Yeah, guarantees that the terms of the series approach 0. Cool. Can absolute convergence guarantee that the terms of the series approach a number other than 0? The answer is yes. Yeah, the number could be any positive real number depending on the particular power series being considered. An example of a series for which absolute convergence of a power series can guarantee that the terms of the series approach a number other than 0. And it did x to the n. Yeah, so the terms of the series approach the value 1 over 1 minus absolute value of x for n equals infinity. Yeah, and this shows that the absolute convergence can guarantee all the terms of a power series approach a number other than 0. Yeah, there you go. Some examples of closed forms for power series. And of course, I long for the day when this will all be shown in nice mathematical notation. Yeah, so cosine, sine, logarithmic, geometric series, exponential series, e to the x, which is x to the n over n factorial. Perfect. Now, this is the hard one. Procedure to find the closed form of a power series. And yeah, this is something that I want to come back to. I found this particularly difficult to work through when I was working on chapter 7. I will definitely be coming back to this particular work, if you want to call it. Procedure to find the radius of convergence of a power series. Ratio test. Yeah. or the opposite of the ratio test, either way. Definition of the Maclaurin series, of course, is for x equals 0. Again, a long description. I love the way ChatGPT does it. Yeah. How can the Maclaurin series be used to approximate the value of a function for values of x outside the interval of convergence of the power series? Yeah. Right. So even if it doesn't converge, it can be a partial sum or a truncated series approximation. An example of a remainder term of a Taylor expansion, of course, this is quoted in Wade, quoted in everywhere that the Taylor series is Taylor formula is proven. Right after, usually someone will quote the error term, and yeah, nice long answer with an example. With an example, very nice. How does the generalized binomial coefficient work? Yeah. Okay, where n is not necessarily a positive integer. Give example. Give an example. Yeah. What are the conditions for a function to be analytic? This is a whole chapter, of course. I mean, a whole section in Wade where they talk about where they prove the Taylor theorem, where Wade, I shouldn't say they. And so, yeah, goes through the steps, goes a little higher with conformality, which is not in Wade. How does the generalized binomial coefficient work in real analysis? Yeah, raising over power to real exponents. That's the whole trick. What are the conditions for a real function, to be analytic? Yeah, if it can be represented by a power series that converges to the function. That's it. What are the Cauchy-Riemann equations or any other conditions relating the real and imaginary parts of analytic functions? Yeah, and of course, this is not in Wade because Wade is doing real analysis. And I even have to admit I forgot why I asked it this question, but now I have it for future testing. And at some point I will be doing complex analysis, so it's going to be good to have. Example of a complex function that satisfies the Cauchy-Riemann equations. I was probably reading something in Rudin when I wrote this. I did these questions several weeks ago. Z squared. Z is equal to x plus iy. And it goes into holomorphic, which is analytic. I haven't studied this yet, so yeah, glad to have this question for the future. Are all functions that are analytic holomorphic? Yeah, so it's a synonym. For complex differentiable in an open set. Okay. Power series of a to the x. And I had already worked on a problem where I had gotten this answer, but I just wanted to check it. Power series for e to the x, which I already knew, but I wanted to see what I would answer. And it gave a pretty good long answer, so that's why I use ChatGPT. Definition of analytical continuation. Extends the domain of definition of a complex function beyond its original domain of convergence. For real functions. Yeah, same deal. Example of analytical continuation of a real function. So it uses the Riemann zeta function. This is the whole thing about the Riemann hypothesis. Example of a nowhere differentiable function that is continuous. It quoted the Weierstrass function, which I had not seen before, and is not quoted in Wade. So I looked it up, and of course there are many ways to do it. All it is you take a continuous function and turn it into some sort of a jagged function, and of course it is nowhere differentiable. It's got jags, uh, many jags, so you can never get it to be to have a slope, right? The more you keep going in, you get that. Yeah. Sorry for the change in contrast. It went from black to white. Then I asked it to plot the Weierstrass function. I put it in Python myself after copying this code, but the way it did it, it just wouldn't plot well. So I changed the parameters, and I asked it to give me the code with those parameters, thinking that it would try to plot it. It didn't. So that's fine. I plotted it myself. But since I already found it, by the way, I'm gonna put this in the description of the video, um, because yeah, so you guys can find it. This is not my plot. I just found it on the internet. Relationship between bounded series of functions and uniformly continuous series of functions. Yeah, so there's got to be a constant m for it to be bounded, and it's the value, the absolute value of the function is less than that number, and there is no strict equivalence. Examples of sequences that are uniformly continuous and not uniformly bounded. Gave me some good examples. Always very useful. And I never have to state how many I need, and it gives me a good number, 3, 4, 5. That's all I was going to ask for anyways. And then I'll end with examples of sequences that are uniformly continuous and are uniformly bounded. Gave me 2 examples. So all in all, a very long session over several weeks going through the infinite series of functions chapter in Wade.